Hello friends, in this lecture today we will see head of a centrifugal pump. So basically there are two types of head in centrifugal pump. One is the static head denoted by HS and the other is a manometric head denoted by HM. So what is a static head? So for that you see this particular diagram I have drawn over here. So you can see the static head HS is the vertical distance between the liquid surfaces in the sump and in the tank. Okay, so that is what the H is. Now the vertical distance between center of pump till the surface of liquid in sump is known as HS, small hs, that is this one. Okay, and this is known as the suction lift as well. Similarly, from center of pump to the liquid surface level in the tank is known as the HD or the delivery lift. Okay, so the H is we can show this as HS plus HD. Okay, where HS is nothing but suction lift, HD is nothing but the delivery lift. Okay, or the discharge lift. Okay, now we will see what I mean by manometric head. Okay, HM. Now manometric head is nothing but the head which is we also called as a total head. Okay, so this is the total head that must be produced by the pump to satisfy the external requirements. In short, the manometric head has to also overcome the various losses. Okay, so if there are no any energy losses in the impeller, that is if there are no any losses in the impeller, then as well as in the casing, okay, as well as in the casing, then the manometric head will be equal to the energy given to the liquid, by the impeller. Okay, or else it also we can say that the manometric head is nothing but the work done by the impeller on the liquid. Okay, now we know that the work done by the impeller on the liquid, that is work done by impeller, that we have seen in the last lecture, which is nothing but VW1U1 upon G. VW1U1 upon G. Okay, so if there are no any losses, in that case this work done is nothing but the manometric head HM. Okay, is known as the HM. If we consider any losses, assume that if we are considering any losses, then the HM is given as VW1U1 upon G minus losses of head in the pump, minus losses of head in pump. So there are various type of losses that we will discuss later on. Now we will see how to get the various expressions for the HM. Okay, so this is what one of the expressions. Similarly, there are so many other expressions too, so that we'll see how to get these expressions. Okay, now we'll see the first expression. For that we will observe this particular diagram. Now what I am going to do, I will be applying the Bernoulli equation at this particular point, that is the surface level in the sump, and the point number 1, which is the just inlet to the pump. Okay, so between these 2 points I will be applying the Bernoulli equation. I will consider this as the datum line. Okay, so I am writing like applying Bernoulli's equation between 0 and 1, between 0 and 1. Okay, so as I'm considering this as the datum line, I will write this as the 0, which is equal to PS by W plus VS square by 2G plus now PS by W is what? The pressure head. Okay, where PS is the pressure at point 1. Okay, Vs is nothing but the velocity through the suction pipe, okay, velocity of flow through the suction pipe, plus Hs. Now if you see, the vertical height between 0 and 1 is the Hs, okay. So Hs plus HFS, that is various losses, okay, various losses in the suction, okay. So that is what the HFS. Now these losses may be either of friction or at the inlet of the pump, which are the minor losses, okay. So from this I can get the equation for PS by W as minus, in bracket, Vs square by 2G plus Hs plus HFS, okay. Now this PS by W is nothing but this suction head, we can say it's the suction head, okay, or the potential head at the suction, okay. So where PS is nothing but the suction pressure, PS is nothing but the suction pressure. Now if you see, the sign for this is the negative, the sign for this is the negative. It means what? There is always a vacuum at the suction, okay, there is always vacuum at the suction, fine. Now suppose suppose if the pump is below the sump level, okay, if the pump is below the level of the liquid surface in the sump, then Hs will be negative, okay, then this particular Hs will be negative, okay, Hs will be negative. So this is how we can get the suction pressure, okay. Now what we will do, we will apply the Bernoulli equation between 1 and 2, okay. So I am writing like this, okay. So we will apply the Bernoulli equation between 1 and 2 now, okay. You observe the point 1 and 2 over here. So this is the point number 1, this is the point number 2. So point number 1 is the inlet to the pump, point number 2 is the outlet from the impeller. So this is the inlet to the impeller, this is the outlet to the impeller. Both are at the same level, both are at the same level, okay. So now we will apply the equation and we will get the Bernoulli equation over here. Now we know that the impeller imparts the energy to the liquid, and that energy is nothing but this particular VW1 U1 by G, okay. So this is what the energy imparted by the impeller to the liquid, okay. So that is what the head, that also we need to consider at point 1, okay, at point 1. So I'll be writing this particular equation something like this. So applying Bernoulli equation between 1 and 2, I'll write at point 1 the pressure is PS, okay. So PS by W plus V square by 2G plus this particular head imparted by the impeller, so that is VW1 U1 upon G. So this is what the head imparted by the impeller to the liquid, so that also we need to consider, which is equal to now I am considering the pressure at point 2 is P2 and velocity at point 2 as V2, okay. So I'll be writing like this. So P2 by W plus V2 square by 2G plus, now as we discussed, these both points are at the same level, but there are some losses in the impeller, okay, there are some losses in the impeller, so that losses I'll be considering as HLI, okay. So this is what the Bernoulli equation between 1 and 2, okay. Now what we will do, we will apply the Bernoulli equation between point 2, which is the just outlet of the impeller, and point 3 is the point in the delivery pipe or in the delivery, okay. So we will apply that equation between point 2 and 3, okay. Now we will apply the Bernoulli equation between 2 and 3, point number 2 and point number 3, okay. So the height between point 2 and point 3 is h. Okay, this is the height between point 2 and point 3. So I'll write the equation first for the point 2. So we know that the pressure head at point 2 is P2 by W plus velocity is V2 square by 2g, which is equal to PD by W plus Vd square by 2g plus the vertical height between point 2 and point 3, that is h, plus as the fluid is flowing through the casing over here, there are some losses, and that losses I am writing with the HLC. Okay, now here the PD is the pressure in the delivery pipe. Okay, Vd is the velocity of a discharge, or the velocity of the flow in the delivery pipe. Okay, so this is what the P2, this is what the Bernoulli equation between point 2 and point 3. Okay, now what we will be doing, we will be adding this particular equation, okay, with this particular equation. So we'll be adding the Bernoulli equation between 1 and 2 and between 2 and 3. So what we will be getting, the next equation. Okay, so what we'll be getting the equation. So first is PS by W plus Vs square by 2g plus Vw1 U1 by g, as it is. So I am writing over here, this is PS by W plus Vs square by 2g plus Vw1 U1 by g. Okay, so that is on the left hand side. Okay, now P2 by W and V2 square by 2g is on the left hand side over here, plus P2 by W plus V2 square by 2g is on the right hand side over here. So both these will get cancelled to each other. Okay, so I'll be getting the right hand side now, that is PD by W plus Vd square by 2g plus h plus this HLI plus HLC. Okay, so this is what the equation I'll be getting after adding the Bernoulli equation between point 1 and point 1 2 and point 2 3. Okay, so here what I'll be doing, I'll be just rearranging the term. Okay, so after rearranging, I'll get Vw1 U1 by g minus these losses I am taking on the left hand side, which is equal to PD by W Vd square by 2g plus h, as it is, minus this particular PS by W plus Vs square by 2g on the other side. Okay, now this Vw1 U1 by g minus these are what the losses. Okay, so Vw1 U1 by g minus, I can say, the loss of head in pump, which is equal to, now this is what the energy, this is what the energy of a liquid at exit. Okay, so energy of a liquid at exit minus this is what the energy of liquid at the inlet. Okay, energy of liquid at inlet, Okay, so this left hand side Vw1 U1 by g minus losses of pump, we know that this is nothing but the HM. Okay, so Vw1 U1 by g minus losses of head in the pump is nothing but, so this is nothing but the HM. Okay, so I can say this is nothing but the HM. Okay, so HM is nothing but, the manometric head is nothing but the difference between the energy of a liquid at inlet and exit. Okay, so this is the one of the expression for the what you can say, the HM. Okay, we'll just further simplify this. Now what we assume that the velocity of suction and delivery, or the velocity of flow at suction and delivery pipe, are equal. Okay, so these Vd square by 2g and Vs square by 2g will get cancelled, as well as if suppose I am considering the point 2 and point 3 are at the same level. Okay, or the gauges applied over here at point 2 and point 3 will be at the same level, then H will be 0. Okay, then H will be 0. So in that case the HM I'll be getting HM is equal to that Hm will be Pd by W minus Ps by W, that is minus Ps by W. Okay, so where I'm considering Vd and Vs are equal and H is equal to 0. Okay, so this is what one of the expression I'll be getting for the Hm. Okay, now we will apply the Bernoulli equation between point number 3 and point number 4. Okay, so applying Bernoulli equation between 3 and 4. Okay, here what I'll be assuming that H is 0. Okay, we'll be assuming the H is 0. Okay, so I'll get the heads at point number 3. So these heads are Pd by W plus Vd square by 2g. Okay, this is what the head at the point number 3, which is equal to head at point number 4, where point number 4 is the liquid surface in this tank. Point number 4 is the liquid surface in the tank. Okay, so if I'm putting the H is equal to 0, point 3 will be on the center line. So I'll be getting the heads as, first of all, that is that I'll be getting as HD, that is what the vertical height between point 3 and 4, plus the frictional head HFD plus Vd square by 2g. Okay, that is what the velocity in the delivery pipe. So Pd by W I'll be getting as HD plus HFD. Okay, HD plus, so Pd by W is HD plus HFD. We know this particular equation for Ps by W, that is minus Vs square by 2g plus Hs plus Hfs. Also we know this particular relation of Hm, that is Pd by W plus Vd square by 2g minus Ps by W plus Vs square by 2g. What I'll be doing, I'll be putting all the values of Pd by W and Ps by W in this particular equation. So Pd by W plus Vd square by 2g minus Ps by W minus Vs square by 2g. I just open the bracket. Then I'll put the value of Pd by W as HD plus HFD plus Vd square by 2g minus, I'll be putting the value of Ps by W, that is minus Vs square by 2g minus Hs minus Hfs minus Vs square by 2g. So HD plus HFD plus Vd square by 2g plus Vs square by 2g plus Hs plus Hfs minus Vs square by 2g. So these two will get cancelled. Finally, I'll be getting the equation for Hm as, Hs plus HD plus Hfs plus HFD plus Vd square by 2g plus Vd square by 2g. Now if the velocity of liquid in a delivery pipe is less, then Vd square by 2g will be neglected. Okay, in that case the Hm will be this equation. So these are what the various expressions for the Hm. Okay, these are what the various expressions for the Hm. Thank you.